Good day, ladies and gentlemen. Welcome to our lesson. Today we're going to be looking at the aspect of stoichiometry. So in chemical engineering, it's pivotal that we understand what stoichiometry is and where do we use it in our calculations and as far as accounting for material balances with chemical reactions. So firstly, we'll look at the definition of stoichiometry. Now, stoichiometry is the application of the chemical reaction equation. So you can see here I've got a chemical reaction equation that just shows us the reactants and the products as well. So the products and the reactants have got coefficients as well. We call this molar ratios. So the use of molar ratios in the reaction equation to determine the amount of product or reactant. So this is what we use. These are the molar ratios, the minimal alphabets A, B, C, and D. And then the A, B, C, and D alphabets, we use them to identify the species. So species A reacts with species B, giving you species C and D. So you can see here, it just shows us that the reactants, when they come into the reactor, what happens is you'll have some reactions taking place, and then what will happen is that A and B will disappear, and then C and D will appear as products. However, you will have the amount of A and B remaining. We call that unreacted moles of A and B, because we find them in the product stream. And then obviously C and D, these are completely new products that have been formed due to the reaction of A and B. So what happens, it's just simplified. You know that your reactants are disappearing, however, your products are appearing. Now let's start with the stoichiometry terminology. Firstly, we have a limiting reactant. Now a limiting reactant is the species that would theoretically run out first if the reaction were to go to completion. So now if there's a complete reaction or complete conversion or a maximum reaction or 100% completion of the reactant or the limiting reactant, we can use that assumption to actually determine the limiting reactant, as you can see as we move forward with our lesson. So basically your limiting reactant would run out first, and it's the most valuable, making it also the most costly, because chances are you will buy your limiting reactant. However, in most cases your excess reactant is normally less costly than the limiting reactant. For example, if you take a clear example of coal reacting, which is fuel, in a combustion chamber reacting with oxygen, that is air. Now you will get the required products and the required heat. However, air can be drawn from the atmosphere, so air is always in excess. So air is always an excess reactant, whereas coal, which is a fuel, will be your limiting reactant. So theoretically, coal during combustion process will actually run out first, as opposed to the air or the oxygen. But remember, this is based on a theoretical assumption, because normally most processes, they don't go to 100% completion in real life. And the second stoichiometric term is excess reactant. We've spoken about this. The excess reactant remains at the end of the reaction, when the limiting reactant has actually run out. So now you will have the excess, still using the same example, is air or oxygen in this case, because you always draw it from the atmosphere. Now, if you look at this layout here, you've got NiO. This represent the initial moles, the moles entering in the beginning of the reaction. These are the initial moles. At the end of the reaction, these are the remaining moles, Ni. So we call that the remaining moles. Once some of the moles have reacted or have been consumed or have been used up in the reactor, you're going to have Ni. So NiO, initially, this is what you have, and then finally Ni, this is what you have. As you can see depicted in this equation here, This here is called maximum extent of reaction. So this is the maximum extent of reaction. It tells you that here we take the assumption that the reaction goes to 100% completion, or the reactants react at a maximum basis or 100% completion. So theoretically, we're basing that everything reacts and we see what happens. Then that's how we can actually determine limiting reactant. So you can see here, this is the first reactant, which is reactant A or species A, and then you've got the second reactant, species B. So both, you're going to determine their maximum extent of reaction, and then the lowest value that you're going to get between the two will give you the limiting reactant. However, the highest value will give you the excess reactant. So that's how now you differentiate, and that's how you get which one is limiting in the reaction and which one is in excess in any particular reaction. Now moving forward, what's important, the excess reactant, normally, how do you signify it? We can even be able to calculate the percentage excess reactant. So the percentage excess reactant is the extremeness of the excess reactant in comparison to the limiting reactant. So the assumption is applicable for complete reactions again. Now you can see here, in this case, the excess was oxygen. So the excess entering, so, subtract the excess reactant required to react with the limiting reactant divided by the excess reactant that is required to react with the limiting reactant. So that's where you get your percentage excess. So we've used oxygen as an example because normally in combustion problems you would always have oxygen being the excess reactant, since the air is drawn from the atmosphere as opposed to the fuel, which has to be bought and it's in limited amounts. And then thirdly, you've got the degree of completion. Now the degree of completion, the DOC, is the ratio of the limiting reactant that reacts to the limiting reactant that is fed in the system. So now the degree of how far the reaction will go can be determined by the DOC. It's also related to the percentage conversion. So how many moles of the limiting reactant can be converted to product. So that's your DOC, or your degree of completion. And then fourthly, you've got the conversion. It can be a percentage or in fractional form. So it's the fraction of the raw material that is converted to product. That is the percentage conversion. Obviously, you have to multiply it by 100 to convert it to percentage. Or you can leave it in fractional form, and that is excluding the step where you multiply it by a value of 100. So conversion, it can be conversion of the limiting reactant or conversion of the excess reactant. Whereas with DOC, or degree of completion, is strictly limiting reactant that you are using. But here you can use either of the reactants that are involved in that particular reaction. And then fifth one, we've got selectivity. Now selectivity is actually self-explanatory. The amount of desired product, that's the ratio, to the amount of undesired product. So normally it's not necessarily an undesired product, but it's a side product or a byproduct that is actually produced in that particular reaction. So you take the ratio of your main product that you want divided by the byproduct that you want, so that you get the selectivity ratio. So moving forward, we've got the yield as well. Now the yield is a ratio of the amount of desired product to the amount of the key reactant fed. Now when you speak of the key reactant fed, we also refer to the limiting reactant. The key reactant is the limiting reactant. So that's very key to actually understand. Now just note that other ratios can be used to define yield. So normally I'll give you and say the yield is actually given in this ratio. It can be the amount of desired product also over the amount of the side product. That can still express the yield, or the amount of another product in the same reaction divided by the amount of the second reactant, not necessarily, or the excess reactant, not necessarily the limiting reactant. That will still be taken as yield. So now, what we should also be able to note, what is very, very key, these things that are mentioned here. You've got coefficients. So in your chemical reaction equation, you've got coefficients. The coefficients are negative for the reactants and they're positive for the product. So the moles reacted, when the moles react, you've got moles consumed, moles disappeared. It's one and the same term. It's just that you sort of used interchangeably. We can say the moles that have disappeared in the reaction, the moles that have been used up, the moles that have reacted, the moles that have been consumed. Okay, and then the reaction equation should be always balanced because we use molar ratios when we're solving problems associated with stoichiometry. So now if you do not balance your equation, you will not get the right values when you are trying to account for the product or for the feed or even for the reactants. Now, what is really, really key, last but not least, don't work with mass convert to moles. Every time convert to moles, because when you work with mass, then you're not going to be able to utilize the molar ratios in the right way. So the advice is first convert all your amounts into, or your values into moles. Then it becomes much easier for you to solve that particular problem. So I hope you understood stoichiometry. I'll see you in the next lesson. Thank you very much for watching.